Hi everyone, Christian Arpariso here to give you a quick introduction to Nastran Solution 200. This happens to be the optimization solution sequence. Now, I want to basically spend very little time in the PowerPoint and spend most of my time showing you how to actually use Nastran Solution 200. But to start off with, there are some key questions I want to address first. These questions come up very often, so I figured it's worth discussing these at the beginning. So these questions should take a few moments to answer, and then the majority of this presentation is going to be focused on the demonstrations. I'm going to start off with a very simple example, and then I'm going to build up to examples you might find in aerospace or automotive applications. Now, just in case you have additional questions after this presentation, maybe you want more training on Nastran Solution 200. Maybe you have a question about its use. Maybe you found a message in a file that you don't know what it is, but you're wondering to find someone who does. You can all contact me regarding this. My email is here in the middle of the screen. Feel free to send me a message and I will get back to you as soon as I can. Now, the first question I want to address: what can be optimized? This is a question I get asked most often. It's actually one of the, how do I say this? One of my favorite questions, because I was there on day one asking myself, okay, what can I actually optimize? So basically, to answer this, you can say it in one statement. If it exists in your finite element model, it can be optimized. Now, what do I mean by this? So here you can see I have two examples, truss A on the left and truss B on the right. You can see that in truss A, there are no members in the inside. So you can see that there. The optimizer will not go ahead and automatically create these elements for you. They have to already exist. So here on the right hand side, you can see that this finite element model, this has the elements that already exist. So the optimizer can optimize those members that already exist. Again, if the entity does not exist, it cannot be optimized. But if it does exist, you can augment it, you can change it, you can improve it. Here's another example, just to hammer this point home. Here on the left, again, the most you have in this finite element model are elements for where you have the support. So these cylinder-looking objects here. There's nothing in here. So there's no expectation that the optimizer will automatically start filling in material for you. That's not how the optimizer works. Here on the right, on the other hand, this is where you have existing material. This is what the optimizer can modify for you. Again, if you have something already defined in your finite element model, it can be improved with Nastran Solution 200. It can be optimized. Now, here, just some general images of finite element models I've seen out there. Really start thinking about how, or rather, what you want to optimize in your finite element model. If it's a structural member, if it's a material property, if it's something that already exists, definitely start thinking of how you can automatically improve it with Nastran Solution 200. Now, there are a lot of optimization types out there. Here I just have 5 of them, but there are a lot more after this. There is global optimization. There's multi-model optimization. There are a lot of other more advanced optimization types, but these are the ones I want to start off with. Now, the first one's size optimization. Basically, if we say that the plate here has a thickness T, and then here, the thickness of the stiffener here, the hat stiffener, we'll say that this is T2. These individual parameters that are dimensions of the structure, essentially, we can define these as design variables x1 and design variables x2, and then the optimizer will vary these two thicknesses, and then you get these design variable plots like you see here in this graph. Now this is size optimization. What is topology optimization? So basically this is almost the same as size optimization, but instead of defining one variable x1 equals t for just the entire plate, it's going to create multiple design variables, one for each element. So here you can have elements 1 equals to t, x1 element el2 equals to t, and then so on and so on for each element. Now this should be x2. So what you end up having are results that you see here. Each element will have a difference in its structural property or dimension. Here you have a thickness 1, thickness 2, thickness 3, and thickness 4. So topology optimization is basically size optimization, but there's a design variable created for each finite element. Now, topology optimization, this is generally used to determine designs that have the highest stiffness. It will identify the most critical load paths in your component, and the parts of the component that are least critical are parts that you can essentially remove material from. So here we have a before with the 0 and then an after with the 1. Now shape optimization. This is basically taking the boundary of a component or assembly and basically letting that vary. So here, for example, you can imagine that this interior surface here that I'm pointing with, well, at least I'm trying to point with arrows. Imagine you're taking this interior surface and you're pushing it in. That's basically what shaped optimization is. If you look at the faces, the surfaces of your component, if you want to push on them, pull on them, shear them a little, you can achieve this with shape optimization. Now, this is different from topology optimization because this is actually identifying critical material to keep or remove. Shape optimization is the changing of literally the shape. Now, topography optimization, basically if you have something that's relatively flat, like this plate, if you will, topography optimization allows the nodes to move out of plane. So basically what you end up having are these almost what looks like a warped surface, but it actually can improve the stiffness for that component. Now, that's a general overview with the optimization types. Again, there are dozens of other capabilities, but since this is a quick introduction, I think I'll leave the other ones for another presentation. Now, what is the magic behind optimization? You'll hear this explained in one phrase, essentially. It's gradient based. Here, just to start off with, I'm going to show you this visually with a graph. What I'm going to do is just make up a quick example right now. Suppose we have a beam cross section, and my drawing game is not good today. Let me go ahead and draw this beam here. Good enough. It's a freshman image. Here we go. So the width is A, the height is B. You can imagine that the weight, if I wanted to, would be A times B times L, which is the length. So I'll draw L here. So suppose that the A, or the width, is going to be represented by x1. And then B will be represented by x2. And then here we have L. And that's going to be constant for this. So suppose we want to minimize W, or the weight. If you recall from calculus, basically part of calculus is towards finding local minimums. So that's what gradient based means. Basically, you're using your regular calculus to find a minimum. So here on the bottom right, I have my what's called an optimization problem statement. First, I have my objective defined. Here you can, for this made up example, you can say that it's weight. And then x1 and x2 are dimensions of the actual structure. My two design variables are x1 and x2. This is again the width A and the height B. The objective is to minimize the weight, or this a function f. And then we have some constraints. This could be stress or displacement constraints. But here, let me go and show you what this actually looks like. And to start off with, we're going to assume that our starting dimensions are 3 and 4 for the beam cross section. So that's 3 and 4 for the width and height, respectively. So here's that graph from the previous example. Again, the beam cross-section example I came up with does not actually give you this graph. It's more of a example to speak with. Now here is the graph. Let's suppose that this function represents function f, which is the weight of the beam. Here, this dot that you see here, 3, 4, this is the starting point of the problem. This is where you have your properties at the initial design, essentially. 3, 4, you have a weight or z value of 25. Now, with a gradient-based optimizer, what it will go ahead and do is it will essentially look and perform sensitivity analysis, or it'll compute the derivatives for this first point. It finds that if you want to minimize this function, you basically have to go down the path of steepest descent. So here again, think about calculus. Here you can see that the optimizer essentially lands at a final value of what looks like 1, 0.05 with the value of z of 1.01. So here, if I wanted to vary the beam cross section to minimize the weight, it would start off at a value of 3, 4, and then it will ultimately end up at a new beam cross-section value of 1, 0.05, and the weight would be 1.01. So that is what a gradient-based optimizer is. There are a lot of requirements for this. For example, your objective function has to be continuous. You can't have any gaps in it. And there are a few other things to consider when you're dealing with the gradient-based optimizer. So now let's go back to the presentation. And now let's move on to the demonstrations. For the demonstrations, we're going to use the Nastran Solution 200 web app. Basically, we are taking advantage of the latest web technology, and we're going to use it for Nastran. This is going to let us take an existing BDF file. It can be a solution 101, 103, 105, and so on and so on. And then it's going to help us cherry pick our design variables. It's going to let us specify our objective. It's going to let us specify our constraints. It's going to let us assign our constraints for each loading case. Then it's going to give us new converted files for Solution 200. You'll find out that there's virtually no need to hand type anything out. Now let's go ahead and jump over to our first example. And quick comment regarding this web app. If you want access to the web app, my email address is here in the bottom of the screen. So if you have any questions on how to access the web app, please contact me here. Now let's go ahead and talk about our first example. This example is going to be regarding model matching. There are a lot of terms for this that I've seen. One way of calling this would have been system identification. Another way of calling this was model updating. And so this is what I mean. I'm just telling you all the different terms just so you know this is what I'm really talking about. But here I'm calling it model matching. So let's talk about the goal. To start off with, I have this cantilever beam that you see here. You can imagine it's fixed on one end and free on the other. I have gone ahead and performed a natural frequency analysis on this, and I found out that the first bending mode is off from experimental tests. So here in orange, you can see this is the first bending mode of this cantilever beam. You can see here at node 1, there's no displacement for the mode, so this makes sense since it's fixed. Now these blue dots here represent what the experimental tests should have given me, but you can see here in orange, we are far from meeting the experimental results. So the goal in this first example is to better correlate the finite element model to experimental tests. And now here on the right is what you see. We're going to change this structural dimension that you see here. I should mention that the structural dimension is a circular rod. You can see that here in orange was the original mode shape, but here in gray is the optimized mode shape. And what's important to note here is that it finally falls in line with the experimental results. So here towards the end of the this demo we will be correlating this model to actual experimental results. Now here is a quick overview of the optimization problem statement. Before any attempt of optimization is performed, it's always good to have this explicitly defined. Basically, let's briefly talk about this. The design variables. Basically, I'm going to let the radius of this yellow section vary. That's going to be my variable. And then my design objective. Basically, if generally, and here I'm just generalizing a lot, what I'm going to try and do for my objective is I'm going to try and minimize this error that you see here. So here it might be good if I do this. So here there's an error for that. There's an error for this. And then there's an error for this point too. So this is going to be my objective. I want to take the error of this, error of that, and the error of this point. I want to minimize that. So that's the objective. Now, what about my constraint? I am trying to correlate two modes 1 and 2. For mode 1, we're going to minimize the error. But for mode 2, we are going to, or mode 3 rather, we are going to try and constrain the error. There, we just want to make sure that the error is within a certain tolerance. So here is our experimental data. So here for each blue point, so here's this blue point, for example. This is a corresponding experimental value. This is the experimental value for node 6 and 9, and then this is for mode 1. We want to do correlation for both modes 1 and 3. So this is all the experimental data that you see here that we're going to need for this example. Now let's go ahead and jump to the web browser because that's where we're going to go ahead and perform the actual demonstration. Now, again, if you want access to the Nastran Solution 2 under web app, basically if you go to theengineeringlab.com, let's go there right now. On the top right hand corner, there is a link called Access. If you click there, this will walk you through the process on how to get access to the web app. Now, let's go ahead and start this tutorial. The first thing I want to point out is the tutorials available in the user's guide. If you come here and go to the size tutorials, you'll see dozens of already crafted tutorials. These are quite extensive. You'll see them cover topics such as multi-model optimization and topology optimization. But today we are performing a size optimization, and here's the example I want to go over. And let me go ahead and download this PDF file. So this is a PDF file you most likely already have. Here I crafted this in Patran. You may have your own program you use to create this PDF file, but what is important here is that you've already created this file. This file is representing this cantilevered rod. So what do we do first? Let's go ahead and go to the size web app, and we'll go ahead and select this PDF file. This is basically the start of the conversion process. We want to take this file and specify our design variables, our objective, and constraints. So here, let's go ahead and look for D. And here we want to modify the radius of section 1, which would be this P bar L1 entry. Let's go ahead and click the plus icon. And here, let's go ahead and look at this and make sure I have the proper bounds I want to specify. So here I want to say that the radius can range between 0.1 and 10 units of length. Let's go ahead and move over to the objective. Let me go ahead and switch to the equation objective. Here I want to create one response for each of these experimental values. So here, for example, node 3, displacement in the third or Z component, I wanted to find a response for that. So let's go ahead and do that right now. So here, let's go ahead and make sure that we click on displacement. So we're going to say that the third component of mode 1 for node 3. So here, A1 is basically representing this first blue point. So this would be this row. This is A1. Later on, we'll go ahead and type in this target value of 0.0143. But for now, this blue point, or rather, it's not this blue point. Well, we've just defined A1 as representing the relative displacement here of the mode shape. So this is A1. This is A2. This is going to be A3. This is going to be A4, A5, and A6. Basically, in a moment, what we're going to do is we're going to say for A2 as an example, 0.1741, 0.1741. We're going to say minimize this error. So that's what we're doing. We're identifying these A2, A3, and so on. So let me go ahead and go back to the web app. I'm going to repeat the process 5 more times. So we'll go ahead and do that one by one. There is a CSV capability. So if you want to do this with the assistance of Excel, you can definitely do that here. But here what I want to do is show you directly how to modify these in the web app. So here, let's go ahead and keep typing this data. And one thing to keep note of, you'll see these status markers or status icons. Basically, if you see a blue icon, it means you've properly configured that row. But if you see a red status icon, that means that the row has not been configured properly. This is beneficial to you because if you try and perform the optimization and there is an error inside of your bulk data file, the optimization will not complete successfully. So this is a sort of validation for you. Let's go ahead and finish this last one. So I've created points A1 through A6, 3, 3, 3, and these should actually be ones here. Right, now let's go ahead and switch over to the match section here in the top right hand corner. Here, this is where I can type in the values regarding the optimization problem statement for model matching. So for example, A1, I want to target the value of 0.0143. I want to match that value of 0.1741 here. And we'll keep doing this here and here, 0.631. And then I want to minimize the error or the difference between the finite element model and the experimental results. And now for A4, A5, and A6, I want to say correlate to a value 0.1204, 0.5431, and 0.9216. And then let's see, I want to target a value of, let me leave this at 0.01 for now. So here's what we're saying again. Here, including the objective, we want to minimize the difference between the FE model and the experimental model, or experimental results for A1, A2, and A3. These three correspond to the mode shape of mode 1. And then for the mode shape of mode 3, we just want to make sure that the difference is within a certain tolerance of 0.01. Now let's go to the exporter. Let's go ahead and download our package. This package contains a small program that'll automatically start Nastran, and it'll automatically generate the plots for you after the optimization is complete. We'll also perform some critical validations. Do you have your license configured? Do you have Nastran properly installed? And so on and so on. There is one slight modification I have to do for this. So I'll go ahead and do that right now, and I'll generally discuss what it is. Basically, mode tracking. Mode tracking, if you will. Now, let me just finish this edit, and then let me start the optimizer. Mode tracking. So suppose you have you have modes 1 and 3, and you've told the optimizer optimize mode 1 and 3. The way the numbers are for the modes, they are in increasing frequency. So suppose mode 3 suddenly jumps to mode 8, but the optimizer thinks, okay, I have to focus on mode 3. If mode 3 jumps to mode 8, but the optimizer still focused on mode 3, it's lost tracking the actual mode. So what mode tracking is, it basically makes sure that it follows the mode. So if mode 3 becomes mode 8, the optimizer knows to switch from 3 to 8 also. So here, let's go ahead and see if we have actual results. Here, the status, I won't cover that. Let's first look at the local optimization results. You can see here, this is our starting error of 14. Towards the end, we have a very small error of 71 times 10 to the negative 9. Here you can see that the dimension actually increases. We start with a radius of 2, and we end off with the radius of 3.92. And now here, this is where we can look at how close we are to matching our experimental results. Here in blue, or the initial results, this is the relative displacement for the mode shapes for the initial design. This in green is our target value. So remember, in the table, I typed in a value of 0.0143, 0.1741. These are the values in green, 0.1741, 0.6381, and so on and so on. Here in orange are the final values. You can see that we have very comparable results. So this is indication that we've successfully performed the correlation for this particular model. So now, that was the first tutorial. Again, this is a very simple example. You can see that the example itself is pretty sophisticated, but the web app makes the process of configuring this very simple for you. Now let's go ahead and switch on to our next example, that of a stiffened plate. So here, let's go ahead and switch over to this example. Here I'm just showing you a profile view. This example actually looks like this. Here we go. Here you can see that we have a plate here, and then we have a stiffened with an actual one-dimensional element. Its beam cross-section looks like what you see here in purple. Now, what do we want to do? We want to vary the thickness of the plate. So here we'll go ahead and call this T1. And we also want to vary the thickness of this beam stiffener. So we'll go ahead and call this T2. Of course, we want to minimize the weight. So by the end of the optimization, we're going to minimize the weight to a 5.45. In addition to this, we're going to have some constraints. Let's see if I have that here. We're going to have a stress and displacement constraints on certain points in the finite element model. So again, that's what the optimization problem statement is. Let's go ahead and start this tutorial. Let me go ahead and close all of these windows. Let me go ahead and start off from the beginning here. So let's go ahead and navigate to the user's guide. We'll go ahead and look for this example. That would be this one here. Let me download the PDF file. And so like before, let's go ahead and upload this PDF file. And let's go ahead and create our first variable. So here we want to optimize the thickness of the plate. So we'll go ahead and select this thickness of P shell 1. And here for the range of values it can vary between 10 or 0.001 and 10. And then we want to vary the thickness of the beam cross section. So we'll go ahead and look for that. So that would be thickness of flange, web, and so on. And here we'll go ahead and give it an upper bound of 10. So this variable can also vary between 0.001 and 10. Now, there is one very special thing about this example, the offset. So here you can imagine that this thickness here is going to increase. So you could have something like this. If it's something like that, you can have it actually interfere with the beam cross section. So we're going to define an additional relationship, if you will. We're going to say that as the thickness increases, so that would be this thickness here, as the thickness increases, also push up or offset the beam cross section. So the benefit of doing this is that you have something that's flush. So if this was the beam cross section, you can see that it would actually move along with the thickness of the plate. So that's the relationship we're going to define right now. So let's go ahead and do that. And so here you have a few ways of doing this. Let's go ahead and find the offset. So W3A and B is what represents the offset of the element. What you can do is you can select that property and then manually type in the relationship 0.15 plus x1 divided by 2.0. So basically x1 is the thickness of the plate, divide that by 2, and then 1.5 is the height of the cross section divided by 2. So this represents the offset relationship. We can manually type this in one by one for each relationship, or we can just type it in this one box and then click this yellow create icon. And then once that happens, it sets all of those properties or offsets with the same relationship. So here I've created these other 7 relationships here without having to type in the equation for each one. Now that finishes the configuration of the variables. Let's move on to the objective rather. We'll go ahead and select the weight as the objective. We want to minimize this. And now for the constraints, we'll go ahead and say that the stress, well, we want to constrain the stress for P shell 1. So we'll go ahead and do that for 1. We'll let that range between, we'll give it an upper bound of 25,000, and then we'll go ahead and do the same for the underside of the plate. So this first one is the top, this next one is the bottom. And we'll go ahead and do this again for the beam cross section. So here, let's go ahead and select this and this. Basically, we're going to say for one end of the element, we want to constrain the maximum stress, and we want to do this for the opposite end, or end B. Then here, 3 and 3, we want to allow the values to range between negative 25,000 and positive 25,000. And we'll use the same bounds for the next one. And then let's go ahead and create our displacement constraints. Basically, we want to constrain a point in the actual plate. We want to make sure that it doesn't deflect a certain amount. So let's go ahead and create this. And then for the first one, this would be node 10302 It's going to range between a value of -1 and 0.1. And then we'll go ahead and do this again for the last constraint. 10203, and this is going to range between -0.03 and +0.03. And now let's go ahead and assign these to our load cases. Here, think of a subcase as a load case. We'll go ahead and assign all these constraints to all the subcases, but given the problem, we just need to remove constraint R6 from subcase 1, and we need to remove subcase R5 from subcase 2. So if I was dealing with buckling, you can also use this to configure buckling constraints if you have those load cases in your model. Now let's go ahead and go to the exporter, and like before, let's go ahead and download this package. And then we'll go ahead and extract the contents. And then while that's happening, let me go ahead and purposely include an error here just to show you the benefits of this web application. Let me go ahead and delete that. And let me go ahead and remove this here. So these are purposely added errors in the model. I want to show you what happens in the web app when this happens. Let me go ahead and start this optimization and let that run in the background. Now, when you go to the exporter and there are problems that are detected, you get these error messages. When these error messages pop up, obviously you're going to have a problem with the optimization. So here, what you can do is simply go to that section. You can correct the problem. So here, 10302. Go back to the exporter, the message is gone, and then here you're getting another message saying that one of your constraints has not been assigned. So let's go ahead and jump here and let's go ahead and assign it to load case 2. And there we go. It's gone. Now this is where we've encountered another problem. Let's go ahead and see if we can find out why we have this problem. Here what I'm looking for is a fatal message. And here I've mistyped one of the identification numbers. So let's go ahead and come here. You can see that here I typed in a 2 that should have been 1. So let's go ahead and download this new file. And then like before, we'll just go ahead and extract the contents and start Nastran. And again, if you would like access to this web app, it's available at theengineeringlab.com. There are hyphens between each word in the name. And then after we're done with this example, we're going to switch to an example you might find in an automotive use case. So here the status page is giving us an update regarding where the optimization is at. And then here we can review what exactly has changed. Here you can see we started off with the mass of 6.96. And we ended off with the noon mass of 5.47. It's important that we have a green message here saying that the optimization went through successfully. Here we see the change of the structural dimensions. We see that the plate went from a thickness of 0.15 to a thickness of 0.11. And here we can see what X2 also changed to. Now that is our example of a stiffened plate. Let's go ahead and move on to our next example. So this example, we have a plate with a frequency dependent loading. We're going to perform a frequency response. And this is basically what we want to do. Here in blue is the initial excitation for a specific point on the plate. So here on blue, this is what you have. What we want to do is minimize the area under that curve. And so what you see after the optimization is the new the reaction, if you will. Here in orange is the new result. So after we vary the thickness of the plate, we have a new frequency response, if you will, and that's indicated here in orange. So here, what we want to do, if you look at the optimization problem statement, we want to minimize the root sum of squares for this point. So the point or the graph you saw here, this is the displacement for this particular point. We want to basically minimize this displacement. One of the constraints, we want to make sure that it's close to the original volume. We don't want something being drastically different. And so after the optimization, this is what we have. We have a minimized or a lower value of the RSS value, and the volume's pretty much the same as it was before. But note that the change in the thickness. Here you can see that the original design basically has a constant thickness throughout the plate. But here you'll notice that the thickness for the new plate is varied, and that's because we are setting these thicknesses as the variables. So let's go ahead and talk about and show you how to perform this example in the web app. So like before, let's go ahead and download this example. This example again has already been crafted in a pre-post processor, and we'll go ahead and use the web app to convert this file to solution 200. Let me go ahead and select this PDF file. And at this point, I think you understand the flow here. Step one, you go ahead and identify all your design variables. So let me go ahead and do that. Step number two, specify your objective. Here, I want to set the displacement, specifically the root sum of squares. I want to do this for the Z component for this node 1110. For my constraint, I want to specify a volume constraint. I want to say that the constraint or the volume should be essentially close to the original value of 8. Here, I don't type in a value of 8 and 8 for the lower and upper bound. I have a slight difference between the bounds. So now let's go ahead and look at this. Is there anything else I want to do here? Then let's try that. Let's go to the exporter and export this. And you'll really notice how quickly I moved for this last example. And that is another benefit of the web app. It's in this nice workflow. Step one, create the variable. Step two, create the objective. Step three, create the constraints. Step four, if necessary, assign these to your various load cases. And here, step number 5, download and start the optimization. And then step 6, you view your results and see what has changed in the model. So we'll give that a few moments while it's going and finishing. And again, if you have any questions regarding optimization, how to use Solution 200, my email address is here in the PowerPoint, here in the bottom. So if you have a comment, feel free to send me an email there. Now let's go ahead and look at our results. So here, first of all, we have the green icon. We've had a successful optimization. We see that the original RSS value started at 15 and it's been reduced to 11.3. Here we see the changes in all the thicknesses that we specified as design variables. Now let's look at the actual plot. So here in blue is the starting displacement curve for that particular node. Since we wanted to minimize the RSS value, this is our new curve in orange. You can see that it's actually been minimized for the most part. So we've achieved the objective for this particular example. So let me go ahead and close that out. Let me go back to the home page of the engineering lab. So that was the last example for this presentation. Hopefully Hopefully you found this presentation informative. If you have any feedback, please feel free to contact me here at the bottom of the screen. My email address is there. I'll leave it posted at the end of the presentation. We've gone over some critical questions such as what can be optimized. The answer to that was if it exists in your finite element model, you can vary that dimension, that material property, and so on and so on. We went over some of the key optimization types in Nastran Solution 200. For most of this presentation, we performed size optimization examples. If you wanted to perform a topology optimization, we also have tutorials for that. And then we briefly discuss what is the magic behind optimization. And here it was the gradient methodology for optimization. Now here, I'll just leave my contact information here just in case you have a question regarding Nastran Solution 200, or maybe you want to start off with structural optimization, or maybe you want access to the Nastran Solution 200 web app. Feel free to contact me here, and I would like to thank everyone for being with me today as we went over a quick introduction to Nastran Solution 200. Thank you everyone, and have a great day.